So we've solved some trig equations together in class, both graphically and algebraically, and this is just going to be another short presentation on solving some of these trig equations algebraically. Alright, so our first equation that we're going to look at here is sine squared x cosine x is equal to cosine x. The first thing that we want to do is we see that this equation is in terms of both sine and cosine, and really we only want to use one trig function. So let's go ahead and rewrite sine squared using our Pythagorean identity into 1 minus cosine squared x. So you can see here that all I've done is rewritten sine squared. Now we want to go ahead and perhaps distribute. We could do that if we wanted to. So we could go ahead and distribute cosine x through. And when we do that, we're going to have cosine x minus cosine cubed x minus cosine x is equal to 0. All I did in the same step was move that one cosine x to the other side. So what happens there is I can see easily that this cosine x, subtract that cosine x, is eliminated, and I'm left with negative cosine cubed x is equal to 0, and I'm simply going to divide both sides by -1, and I end up with cosine cubed x is equal to 0. Well, if you think about that and you want to go ahead and pursue the cubed root of both sides, you know that with that said, the cosine of x is also equal to 0. Now you want to consider where that happens on your unit circle. Well, on your unit circle, if you're thinking about your unit circle, remember our cosine is our first coordinate, and our first coordinate is going to be 0 at up here at pi over 2 and down here at 3 pi over 2. And with this, we could certainly write what we're comfortable with. We could say that x is equal to pi over 2 plus 2k pi, because the period we know of cosine is 2 pi, and that x is equal to 3 pi over 2 plus 2k pi, because I didn't specify the interval that we were going to be working on. But notice that if we go exactly pi units each time, we're going to be at a position where cosine is 0, so we could condense our answer, and for a final we may just say x is equal to pi over 2 plus k pi. And this is something that's a really good technique if you understand that it really is happening every pi units. So go ahead and look at this equation that we're going to be solving here. 2 sine squared t is equal to 3 cosine t. See if you can pause the video and do a little bit of work on your own before you restart the video and see how I pursue it. Alright, so if you pause the video, hopefully you were able to at least get through these first two steps. In this first step, all I did was take and rewrite sine squared as 1 minus cosine squared. In the second step, I distributed 2 through my parentheses. Now in my third step, I'm going to kind of rearrange things a bit. I'll have 2 cosine squared t minus 3 cosine t plus 2 is equal to 0. But I don't know about you, but I don't like to start looking at my quadratic there with a negative leading coefficient. So I'm going to go ahead and divide off a -1, and I'm left with cosine squared of t plus 3 cosine t minus 2 is equal to 0. And some of you may be thinking, why am I putting parentheses around the t? Not for any reason other than the fact that it oftentimes, when I'm using t as my variable, it looks like cost. So the t is really there, or the parentheses are there just to separate for you. The next thing that we're going to do is we're going to notice that we do have a quadratic that we're working with, and off to the side, I think I'm going to be thinking about 2x squared plus 3x minus 2 is equal to 0. And I'm really just writing that equation in terms of x's to mimic what we have in our cosine equation. And what we're going to do is just quickly look at how this would factor, and then we're going to use this idea when we go to factor our real equation in cosine. So I know that 2x and x are certainly going to be the leading terms in my binomials there. And then I believe I'm going to have a 2 here, a 1 here. Looks like this one needs to be plus and this one needs to be minus to end up with our positive 3x. And you can double check that and make sure that you're understanding there. Now I'm going to come back to my cosine function, and in my parentheses I'm going to put 2 cosine of t, right? 2 cosine of t in the first parenthesis, first term, and then I would have cosine of t in my second parenthesis there. And then I know that, again, here I'm going to have my plus 2, and here I'm going to have my minus 1. And so that really sets up nice for you to be able now to do your factoring. And what we are going to do with these factors, remember each of these factors is going to be set equal to 0, and we're going to solve them independently. Okay, so let's finish our solution to number 2. So really all we're going to do here is we're going to take each of these factors, and I'm going to say 2 cosine of t. I'm going to go ahead and add 1 to each side is equal to 1, or cosine of t, subtract 2 from both sides, is equal to -2. Well, when I look at this, one of the things that I recognize right away is that I'm never going to have a cosine of t equal to -2. So that just tells me there's no solution for that little piece. But over here, I can continue working, and I'm going to divide both sides by 2. So now that tells me that the cosine of t is equal to 1/2. And now we could just, again, if we refer to our unit circle, we know that we're going to have the cosine of 1/2 that's positive in quadrant 1, and in quadrant 4, here we've got the point 1/2 square root 3 over 2, and down here we have 1/2 negative square root 3 over 2, and we know that our cosine is our first coordinate. So now we could come back and go ahead and write our solution for t. So t there is going to be equal to, in our first quadrant, that's going to be pi over 3 plus 2k pi to pick up all of the different rotations, either in a forward position or in a reverse position, right? That'll pick all of these up that we need. And the other one that we want to consider, well, down here in the fourth quadrant, that one is going to be, if we are remembering how to work with our reference angles, if we don't have our unit circle handy, we know that it's basically going to be 2 pi minus pi over 3, and that's going to leave us with 5 pi over 3 plus 2k pi. Okay, so let's take a look at one now where we will use a trig identity to help us solve it. So go ahead and look at this. Cosine 2x cosine x plus sine 2x sine x is equal to 1. Pause the video and see if you can find a trig identity that will help you solve this equation. Alright, so you can see the identity that I think would be best to use on this, and this is the cosine of a minus b. Notice that this right side of our identity matches up with the left side of our equation. So we're going to identify a as 2x and b as x. And if you notice, that's consistent when we move over here to sine. So now the first thing that we want to do is basically condense it and write the cosine of 2x minus x is equal to 1. So again, if you are not understanding how that identity is being used, please make sure that you go back to some of the other lessons from Unit 2 and look at that. Then we're going to simplify this a bit more. This is just going to say the cosine of x is equal to 1. And we know exactly where the cosine of x is equal to 1. That's going to be at x is equal to 0, 2 pi, etc. So we want to go ahead and write that, and we could just basically say x is equal to 0 pi plus 2k pi. Alright, this concludes this short video. Hope this helped a little bit more.